Hello everyone, I am Zixuan Wang, a PhD student at UC San Diego, and I'm working with Professor Jishen Zhao and Professor Steven Swanson. Today I'm going to present our paper, Characterizing and Modeling Non-Volatile Memory Systems. In this project, we build a profiler and a simulator for non-volatile memory and open source them on GitHub. This work is initially published on Micro 2020 and recently selected by IEEE Micro Topics. Non-volatile memory is a type of main memory that sits on memory bus and provides better addressable access to CPU, just like traditional DRAM-based main memory. It also provides data persistence, so the data written into non-volatile memory can be recovered after a system reboot. Intel Optane is the first commercially available non-volatile memory product, and we can buy it now. But why do we need a new simulator and a new profiler? Architecture-level non-volatile memory research usually requires a memory simulator, but we find that existing simulators are not accurate enough compared to Intel's Optane persistent memory DIMM, so we need a new simulator. But non-volatile memory is not just a slower DRAM. As shown here, DRAM latency is stable, while Optane DIMM latency is not constantly slower than DRAM. So we need a new profiler to discover a complex microarchitecture design. Here is how the tools work. We first profile the non-volatile memory with our profiler, lens, and find microarchitecture level observations. We then configure VANS based on these profiling results. And finally, the VANS simulation is good to go. Here is a detailed picture of lens and VANS. Lens is a low-level profiler for non-volatile memory systems. It has carefully crafted micro benchmarks that trigger specific hardware behaviors and discovers the complex microarchitecture design of non-volatile memory products. It also achieves low-noise profiling results. Based on lens profiling results, we build VANS, a validated architectural non-volatile memory simulator. VANS performance is validated with Optane DIMM. It has verified DDR4 model for on-DIMM buffers and can be integrated to Gem5 for full system simulation. VANS provides a general non-volatile memory model that can be reconfigured to simulate other non-volatile memory products. Lens and VANS are open sourced on GitHub. Here is an example of how to use Lens to discover the non-volatile memory buffer sizes. More examples can be found in our paper. On the left is the non-volatile memory system architecture. There are CPU cores, a write pending queue in integrated memory controller, and media chips on the non-volatile memory DIMM. That's all we know from publicly available information. Now, we use a pointer tracing access test with 64-byte block sizes to discover the buffer sizes. As shown in this figure, the x-axis is access region size, and y-axis is latency per cache line. We measure the read and write latency separately. In this test, the read latency starts to increase from 16 kilobyte region size, which means there's a 16 kilobyte buffer overflows at this point. We denote it as a 1 buffer. For the same reason, there's a 16 megabyte L2 buffer. The L2 buffer latency is about 100 nanoseconds, which means it's inside the DRAM. The write latency starts to increase with 4 kilobyte region size. This indicates a low store queue on non-volatile memory DIMM that performs request reordering and write combining. The write latency drops until 512 byte region size, which indicates the size of write pending queue. Now, let's take a look at VANS. VANS is a cycle-level non-volatile memory simulator that is flexible and reconfigurable. It can execute memory traces and can be integrated to Gem5 or other cycle-level simulators for full system simulation. VANS is written in C++ 17 standard with a modularized software design. More importantly, VANS can be configured using a simple configuration file without any change to the source code. Here is an example of VANS non-volatile memory model. It has an on-DIMM low store queue that reorders requests and performs write combining. There's a read modify write buffer, which we refer to as L1 buffer in the previous slides. There's an address indirection table stored in undimmed DRAM that handles the wire leveling and address remapping. There's an AIT data buffer stored in undimmed DRAM, which we refer to as L2 buffer in the previous slides. And finally, there is a media model to simulate the non-volatile memory media. WANS also provides a powerful and easy-to-use testing framework to help the users verify their model accuracy. The user can define a test with a simple configuration file. Then, the testing framework automatically generates a set of memory trace files according to the configuration file and run the simulation in parallel. After all tests are finished, the framework automatically collects all the results and generates a report. Here's an example report generated by the testing framework. It shows performance comparison between simulation and obtained DIM, and plot all the internal hardware counters inside the WANS simulation. More importantly, all these testings are automated. The user just needs to set up a configuration file and then use this one line of Python command to run the tests. We believe this helps users to quickly develop their own non-volatile memory system model. We verify the WANS DDR4 model using Micron DDR4 verification model with Cadence toolchain. For non-volatile memory model, there is no formal verification tool, so we match the micro-benchmark performance on the obtained DIM. Here are the validation results using pointer tracing micro-benchmark on single DIM and interleaved 6 DIMs. We notice the WANS latency numbers and curves match the obtained DIM very well. We also take the hardware counters from obtained DIM and WANS to calculate the rate amplification for L1 buffer. As shown in the left figure, the amplification factors match very well. We then perform the override test on WANS and find its long tail latency match the obtained DIM. In summary, we first build Lens Profiler. It contains a set of customized micro-benchmarks and use them to discover the complex microarchitecture design of non-volatile memory products. Based on lens profiling, we build WANS, a non-volatile memory simulator that matches Intel obtained persistent memory DIM's performance. It contains verified DDR4 model and validated non-volatile memory model, and can be integrated to Gem5 or other cycle-level simulator for full system simulation. Lens and WANS are now open sourced on GitHub. Due to the time limit, we cannot present all the details. For more information, please read the paper and watch the full talk video. Thank you.